Now that we have some geometric intuition behind what eigenvectors and eigenvalues are, let's move on and discuss how can we numerically compute eigenvectors and eigenvalues if the transformation matrix is given. Now, algebraically, the concept of eigenvectors and eigenvalues can be described by this equation right here. So, what we are doing, we take a eigenvector, we multiply that by a transformation matrix M, and that results essentially in a scaled version. Lambda is a scalar multiplied by the original eigenvector itself. So, if this property is satisfied, we essentially have a eigenvector associated with a transformation matrix. Okay. So, here in this notation, essentially in this equation, we have M denoting the transformation vector, a transformation matrix, V is denoting the eigenvector, and lambda is essentially denoting the scalar eigenvalues. Okay. So, what this equation says, that the matrix vector multiplication gives the same result as scaling the eigenvector by a factor of lambda. So, if I multiply the vector by m, this results in the scaled version of the vector by the magnitude of scalar lambda that we have here. That is what this equation says. Okay. So, finding eigenvector and eigenvalue is essentially finding out the vector v and lambda which satisfies this equation. So, the question is, how do we numerically compute this if a transformation matrix M is given to us? So, let us get through some steps that are needed and a condition that is needed for us to find out the exact values of the lambdas and v, vector v, which satisfies this equation. So, in order for us to first of all simplify this equation, because on the right hand side we have a vector which is multiplied by a scalar, one simplification that we do is in order to reduce and bring this equation into a form that could be easily used for computation is we multiply both the sides by an identity matrix. Okay, so if I multiply the left hand side by an identity matrix right here, and if I multiply lambda by an identity matrix, that is the next step that will be done. And when we are multiplying that, the effect of multiplying an identity matrix with M is going to result in M, so it's not going to change, but lambda dot I is going to come on the right hand side. Now, what we can do is we can bring the right hand side to the left hand side and equate the right hand side to be equal to a 0 vector, and the the number of dimensions or the elements on this vector is essentially going to be same as the number of elements that you have in the vector v. Now, from here we can simplify this equation and we can write something like this, which is M minus lambda I identity matrix multiplied by vector v is equal to 0 vector. Okay. Now, as we know that if we have something like this, where I am transforming, we have a transformation matrix which is given by this matrix M minus lambda I, and that is multiplying a vector, and that is becoming a 0 vector. What is happening? A vector which might be of any shape is essentially becoming and shrinking to a single point, right? So, after transformation or after multiplication with this matrix M minus lambda I, this vector is essentially shrinking in size and becoming a single point which is located at the origin. Now, when this conditions will be satisfied geometrically, if you understand this geometrically, the only place, and this is something that we have discussed in the previous classes, only condition that this might satisfy, if I take the determinant of M lambda I, M minus lambda I, and the determinant of that is equal to 0, then we will be able to take a matrix, take a vector and squash into a single point, because the singularity exists only in this case. So, what is going to happen? That this condition is only going to be satisfied when this condition is going to be satisfied. So, this can be done by 0 determinant from the transformation matrix. So, essentially we will use this condition, which is determinant of M minus lambda I equal to 0, and that will help us in identifying the lambdas or lambda associated or different lambdas that are associated that satisfy this equation, and based upon that we can first find the eigenvalues, and then we can use these equations that are on the top to find the eigenvector. So, that will be two steps. First, the eigenvalues will be found out using this equation, which is also known as characteristic equation, and we will talk about that, and from there we will go back and use this condition to find out the vector v. So, let us take an example problem and go through all the steps that we have discussed, which will be help us in computing the eigenvectors and eigenvalues in a numerical approach. Okay, so what we have, let's take the same transformation matrix that we have been using. Let's say this is the transformation matrix that we have, and if you want to find out the eigenvalues and eigenvectors corresponding to this matrix, then what we can do, we can start with the equation that we have, right? This is the vector equation that we need to, this equation has to satisfy, this matrix has to satisfy in order for us to find out the eigenvalues and eigenvectors. So we write this, but we know that this will be only satisfied when the determinant of m minus lambda I is going to be equal to 0. So we can simplify up to this location, and now why we got lambda 0, 0 lambda? Because if I take lambda times I, okay, we know that this will be lambda 1 0 0 1, which is the identity matrix. So if you simplify this, we have lambda 0 0 lambda, and that's how from lambda I, which is right here, right, we are getting this matrix using the information that I have just written here. So that's the simple substitution that we are going to do, and we will arrive at the equation that we have on the bottom right hand side that you see on your screen. So we essentially will come back to that equation, and then we will proceed with the next set of equation which will use this equation to solve and find for eigenvalues. Okay, so this will be the equation that will be simplified. So I can take this and I can subtract individual elements. So 2 minus lambda, 2 minus 0, 0 minus 0, and 1 minus lambda, and that will give me this resultant matrix which I can use. And then what is the condition? That matrix has to be equated to 0. So the determinant of this matrix has to be equal to 0. And when this is satisfied, you essentially are taking any vector and you are squeezing and making it to a singular point, and that's the condition that needs to be satisfied here. So in this case, if you take the determinant of this matrix, you will essentially reach this equation, and here from here also you can solve the overall equation, and we can see there are two values of lambda, which is lambda equal to 1 and lambda equal to 2, that is going to be satisfying this equation. But if I want to take this step, right, where I want to write that in the quadratic form, so you can see this determinant is essentially leading to a quadratic equation, and we know that we are going to have two roots for this quadratic equation. It turns out we have the factorization above, so from that factorization we are able to find out the roots of this equation. So the roots of this equations are going to be essentially lambda equal to 1 and lambda 2 equal to 2. From here, if I substitute this one equal to 0, I get lambda equal to 2. If I substitute this equal to 0, I get lambda 1 equal to 2. And those are the two lambdas or two different eigenvalues that will be satisfying. Now what we need to do is, since we got two lambdas which are different values, corresponding to each of this lambda, which is lambda 1 and lambda 2, we have to find out the corresponding eigenvectors, the first eigenvectors and second eigenvectors. One way to process this information is that there are two eigenvalues that are associated with the equation, with this transformation matrix that we initially began with, and there must be two different eigenvectors corresponding to each of these eigenvalues. Now, as I mentioned, this is step 1. We found out the eigenvalues. Now let's take this eigenvalues and then reuse the information that we previously have in the matrix form, in the vector equation form, and find out the corresponding eigenvectors.